Alright, let's get started. Today we're looking at Chapter 8, and Chapter 8 is all about sorting and searching, which is part of data structures, and it is chapter number 8. And by the time I finish today, I'm also going to hopefully remember to talk about the midterm and also the CSLO that I've uploaded. But let me do the chapter first, and then we will continue forward. So this particular chapter, we're examining linear search and binary search algorithms. So it's not what I would call a data structure, but it works with data structures in terms of algorithms and data structures. Examining several different sorting algorithms, and here are the ones that we're going to look at: selection sort, insertion sort, bubble sort, quicksort, and merge sort. The sorting algorithms are not too bad. They're actually quite logical, and they're very intuitive in terms of how they sound. They're descriptive of how they sound. We'll also discuss the complexity of these algorithms and compare one to the other and see what one is good for and what the another one might be good for. In terms of searching, sorting is the problem of finding something. Sorting is arranging the list, arranging the data structure in a particular order. Searching is finding, which is intuitive again. So, the definition according to the textbook is the process of finding a target element among a group of other elements. So the search pool, or determining if it's in there or if it's not in there. Is an item found or is it not found? So it requires repetitive comparing of the target candidate to a search pool. An efficient sort performs no more comparisons than it has to in order to actually complete its task. Same thing with a sort and a search. You don't want to search everything when you don't have to. And you don't want to sort everything if you don't have to. If it's already pre-sorted or partly sorted, you want to use what you have available to you. So the size of the search is the factor, the search space in terms of the calculation. It is going to determine how searchable, or how fast, or how efficient a particular algorithm is going to work. So the goal of a lot of these algorithms is to make the search space smaller. If it's smaller, you have fewer items to search through, faster, more efficient algorithm. The big O notation is a lot smaller. The big O, calculation. So the comparable interface is what Java uses to compare objects, to see if this is an instance. Is this object an instance of that object over there? The comparable interface is what we're going to look at in terms of object 1 compared to object 2. So the Java facility actually has it really built in for you. So we wanted to find an algorithm such that they can be searched through any sets of objects, so we can do what's called upcasting, to take one object and turn it into another object. And then everything's an object. So if we have different objects created of items in a list, and they're all, well, usually lists themselves could contain all like items, but they don't have to. If, for example, we had a list of people, and some of the people were objects of teachers and some of the people were objects of students, we could sort the list alphabetically by their name by turning them all into people or similar objects, and then compare one object to another object in terms of how we accomplish that. So sometimes you're taking objects, treating them like other objects or comparable objects, and then comparing one object to another to see, is this one larger than, or is this one smaller than, or how does it fit in terms of the comparison? Oh, thank you. So, therefore, we're going to use the comparable interface. It contains one method, compare to, as we've seen in the slide here, designed to return an integer that specifies the relationship between the two objects. So if object 1 compared to object 2, it will return a number less than, the call returns a number less than or equal to or greater than 0, depending upon if it's equal, if it's greater than, or if it's less than. So object 1 is less than, equal to, or greater than object 2, respectively, which gives us the order. So here's another example of the comparable interface. So all of the methods represented in this particular chapter of this particular book are going to be static methods of the sorting and searching class. You can actually download the author's source code for this as well. The class makes use of the generic type T. So we are essentially taking T, extending comparable with it, and then we have super T, which is going to be the superclass, subclass is going to be comparable. So those methods that make the further distinction that T extends comparable in terms of our static method. And don't really be concerned about the Java code if it doesn't make any sense to you. It's the concept that you want to get out of this, and you can always take a look at the code later and go through it line by line and sort of dissect it. If you go to the author's website, you can download it. So it's all based upon the same example. So maybe after a few more slides, it might actually start coming into view for you. So the comparable interface means that the array of type T must contain objects that are comparable to each other in the array. This may mean that they are all the same class or descendants of the same ancestor. So a call to such a method would appear such as sorting and searching dot. The method is linear search with a target array and a minimum, a maximum, and then the target list essentially to sort it to. So let's talk about linear searching. Just as it kind of describes, it's going in a line. Linear search simply examines each in the search pool, one at a time, until either the target is found or until the pool is exhausted. So if we have 10 items, it starts with number 1, goes to number 2, goes to number 3, all the way to 10. You can possibly imagine this is very slow, not very efficient, but very easy. So one advantage is it's very simple. You can take an array of items that are indexed 0 through 10, run them through a for loop, and you're basically doing a linear search when you're comparing the first one to the second one, the second one to the third one, etc. So the approach does not assume that the items in the search are in any particular order. They can be in any order. So you don't have to you don't have to sort the items before performing the linear search. You can do it on a raw list of anything. You just need to be able to examine each item in turn in a linear fashion. So it's fairly easy to understand and not very efficient, obviously. So the easier it is, the less efficient the algorithm ends up being in the long run. So we start at the beginning. We compare the first one to the second one to the third one and fourth one. That's why we're getting that linear approach to it. And here's some, using this example again with a comparable T, a generic object. In the class, we're going to find the minimum, maximum, so we can find the biggest. In this linear search, classic problem scenarios, let's find the biggest item in the list, or find the items that match, or find an item is checking to see if an item is in the list. Because if you're checking to see if an item is in the list, you actually have to look at each one of the items. So, and in order to compare all of the items in the list with each other to figure out if it's a maximum or a minimum value, could you check that for me? That would also be an application for a linear list. So, long story short, whenever you have to actually look at every single item, linear makes sense. So, here's some code to look at finding the minimum, or I believe the minimum or maximum. So, I don't actually like the code examples in the slide set. So what I'm going to do is probably, not next week, but the following week, bring in some searching, just like I did for the array list and the queues and the stacks and stuff. Bring in some searching. Example of each one of them and show it to you. If we don't do a linear, we can do what's called a binary search. And I've actually kind of mentioned this one already, but here's the formal introduction to it. So it's a search that is sorted. So in order to do a binary search, we have to sort the list first. So we can't do it on an unsorted list. It's impossible. Because the concept is we sort it, and then we start hacking away at it to make the search space smaller. so the pool is sorted, and we can do more efficiently. It's a more efficient algorithm than the linear search, because if we sort it, we know where items are in the list, and then we can work with parts of the list and forget about the other parts of the list. We don't have to go through every item in the list. Binary search eliminates large parts of the search space with each comparison. So instead of starting at one end and moving to the middle, we start in the middle and we move to the outer ends. So if the target isn't found, we know that it is not in the pool at all, and so we can look at the other half of the pool. It's binary, meaning it's two. We split the list in half, then we split the list in half again, then we split the list in half again to divide it out. So we can jump to the middle to that half, and then continue similar to another half. So as an example, if we started in the center right here, we can say, well, we're looking for the number 20, and we can find out what this number is right here, and say, well, if this is sorted in a numeric order, we know all these numbers are lower, and we know, let's say this number is 30, and we know all these numbers are higher. So we can come back and say, well, it's not going to be higher than 30, 20 is less than 30, so we can get rid of this, take it out of the search space. Now we go 1 through 30, and we look at the middle, and we say, well, what's a 1 through 30? Well, we're going to get 15. We're looking for 20 to see if it's in here. If it's higher than 15, yep, so now we got rid of this path, and then we get from here to here. So as each comparison gets evaluated, the search space gets cut in half. So we're going half, 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 which is why they refer to it as a binary search, because it gets cut in half. That's actually the most efficient search, because as you're searching, you're actually reducing the search space at the same time. So you can't get any more efficient than that. In terms of the binary search, as an example, here is I just explained it to you. This is the slide set's explanation of it with some numbers. So hopefully the logic is going to be reiterated for a second time, so hopefully it'll make sense eventually. So for example, if you find number 29 in the following list of sorted numbers, actually number 29 is right there, but we're not going to start. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so we'll be around 5 or 6 depending upon where we're going to start, and then we're going to go this way eventually. So you compare the target to the middle value, which is 54, and we know that 29 is in the list, and it's in the front half of the list now, because if this is sorted in a numeric order, then these numbers are always going to be higher than 54. So it doesn't have to be, and this is the common mistake a lot of students kind of think, it doesn't have to be a full list in full order. As in this particular example, we have huge jumps and we have lacking, but we're just trying to find if it's in there. So we're searching to see if that number 29, is actually in there. It happens to be in there, actually. So with one comparison, we've eliminated half of the data. And then we compare it to 22. We pick the middle, and then we say nope. And then we compare it again to whatever we have left, and we're going to find it, essentially. So we can compare 22 and eliminate another quarter of the data as well. So the binary search is often implemented recursively. So last week we talked about recursion, because if you think about the concept, we're sending the whole list. Let's say we created a recursive function that does a binary search, and we send it a list and we send it a number we're looking for. So we send it that list and we send it 29. Then it could take the whole list and cut it in half and send it to a function again and say, well, do the same thing. We're still looking for 29, but now the list is smaller. And then do it again, and eventually we're going to find it, and the recursive function is going to stop. So we can add that in with a recursive call. Each recursive call searches a smaller portion of the search pool. The base case of the recursion is running out of viable candidates to each one of the searches, which means the target is not in the search pool if it's eliminated. So at any point, there may be 2 middle values, in which case either one of them could be used. So you can go left or right. You might end up, a list that only has 2 values in it, so then you can go left or right. So depends upon, and if you think about that concept, even if you had to search every item and there were 3 items, still faster than searching 20 items or more. So there's an implementation of the binary search, and again, I'm going to take the source code with a grain of salt. Data, we have the minimum, the maximum, the target. We're going to say, is it found? We're going to set it to false, so we have a little boolean. Find the midpoint, take the minimum and the maximum value, divide it by 2, determine the midpoint. You go to the midpoint, is it less than or greater than the midpoint? If it is, if it's greater than or less than, follow one of these 2 targets that are essentially going to split the list in half again and follow through recursively till the end. So let's do a simple comparison between the linear search, which we've seen so far, and the binary search. On average, linear searches would examine into the, I think that was supposed to be into the 2 elements before finding the target themselves. Therefore, linear search is a big O-N. The worst case in a binary search is going to be a log2n comparison, which is going to be a lot faster, actually. So the binary search is a logarithmic algorithm versus a big O. So in terms of its time complexity, it's O log 2 to the n if we put it in big O notation. But keep in mind that search pool must be sorted. So we have the efficiency on the search but we have another step we have to do prior to that to sort the list. We actually have to sort the list, because if we don't sort the list, there's no guarantee that the binary search is actually going to give us correct results. The number could be in there, but it's not in the right order. So for large n, the binary search is much faster if we have large n values. In terms of sorting, so now we're going to say, well, we're going to do a binary search, but we're going to sort the list. Well, there's different techniques to sort the list. So sorting is the process of arranging a group of items into a defined order based on a particular criteria. So something in the item. So many sorting algorithms have been designed. A couple of them we can look at would be the sequential sort. It requires an approximation of 2 to the n comparisons to sort the n elements, sort of like a linear. It's a sequential sort, sequentially going through the list and sorting each one of the items and placing it in a particular order relative to the other items. Logarithmic sorts that typically require n to the log to n comparisons to sort n elements. So let's define a generic sorting problem that any of our sorting algorithms could possibly solve, and then we'll apply the different algorithms to the problem solution to kind of see how they differ. As with searching, you must be able to compare one element to another, so you have to use the comparable object in terms of the implementation if you're going to use objects for this. Considering that we're sorting and searching objects, we could apply the same concept to numbers. It would be the same principle. Here's the sort phone list class. So we have a phone list, regular old directory. We're going to sort it by name or something, I think, in his example. So create an array of contact objects, sort them, and then print them out. So in main, we're going to create some contacts, some friends, and then it's going to be an array. And here's some contacts: first name, last name, telephone number. And then we're going to apply this algorithm, this method, to do a selection sort on friends as the object. This is going to be a sort and a sorting algorithm. So for index is equal to 0, index less than the length of the friends object, print out the friends index. So print it out to the screen. And we have the, that was the main method actually. The contact list itself is going to essentially be an object that holds a contact, which is a first name, a last name, and a telephone number. And in the contact itself, we'll have a toString method and a compare to, because we need to be able to compare one object to another. So generally, you'll find the compare tos in the classes for the implementation of the objects. And it's the ability to compare one object to another object. So it's taking an object type, and it's using a comparison either on the name, or the first name, the last name, or the telephone number, some component, some piece of data that's stored in the object, which is why it makes sense to put it in the object's implementation to have the compare to. You also normally find the toString in there too, because if you don't put it in here, then every time you use this object out in main, you keep repeating all that information. You keep doing another compare to, you keep doing another toString. So the concept is do it once and then call the methods from the class, essentially, which makes it a little bit more efficient in design. However, it doesn't matter where you put it. It will probably still compile and still run for you. So it's like, but one of the goals of programming is to make it less work as possible, hopefully. So the more efficient you make it, the less work you actually have to do. So let's take a look at our selection sort. So the selection sort orders a list of values by repeatedly putting a particular value into its final position. So it's kind of like when you take a whole bucket of stuff and you pull something out of the bucket and you say, it's the number 5, and it's like 5 is the last number. And you pull the number out of the bucket and it's the number 12. Oh, so 12 is now the last number. So you're ordering it sequentially. Let's say you're putting the list in numerical order. You keep adding it to the end of the list until one, essentially it's the biggest one, and the biggest one, the next biggest one. Which is more specifically find the, and this is going to do the opposite. I just did the biggest one. Here we're going to find the smallest value in the list as an example. Switch it with the value in the first position. So you can sort from small to big, from big to small. Find the next smallest value in the list. Switch it with the value in the second position. Repeat until all the values are in the proper position. So You're ordering it in terms of the relative positions of the first entry or the last entry, depending upon how you want to do it. And this is called the selection sort. And again, you could possibly imagine it's going through the entire list, just selecting each individual item, because you have to do a comparison with each individual item. So you scan the right starting with 3, and 1 is the smallest, so you exchange 1 with 3. Put 1 over, so now we got 3 and 1. And then we look at the next item, 9, and you go, well, let's find the smallest 2. So 2 comes over here, 9 goes over here. Because eventually what you're doing here is you're fixing the order as you're going through the list. So if you swap the items, what I gave you originally with the bucket was when you didn't have the items, but you were just pulling them out at random. If you pull all the items out, spread them out on the table, put them in a line, and the items aren't sorted, you're sorting it while you're sorting. It's kind of like what people do with puzzle pieces sometimes. They take all of the green ones and they stick them over here in the red. Well, there's a little piece of red. It looks like it's part of a tree. Put it over here. You're actually doing that with this because you're selecting it and you're doing the sort by a selection. So if you know that this number is bigger than this number is going to end up over here. It might actually move, and what you get with this is unnecessary moves. Or not unnecessary moves, you get repeated moves. So this number 3 isn't going to be over here. The number 3 is going to be switched here. It's switched down here actually. But this is a safe bet. This is going to save you a lot of time in the end because 9 is the last number. It just happened to have been over here. If 2 were here, then 9 would have been here, then 9 would have eventually been moved over here. So it's kind of unpredictable in terms of the number. The more sorted the list, the fewer number of swaps. So it's efficient in terms of if you have a partly sorted list, it doesn't make as many adjustments. And the adjustments are time consuming. So you scan, here we get the 9, the 2, we'll swap them. So now the 9's over here, the 2's over here, swap the 6 and the 3. Look at the 6, we're good. We're basically done. So this was done in three moves, essentially, instead of 1, 2, 3, 4, 5 moves. So if we did a linear sort on this, instead of a selection sort, we would have done 5. So we cut it down to 3 moves. So. And here's our selection sort in terms of our implementation, and we have, this is the code I'm going to skip the code. This is the code that goes along with it. I don't like those code examples. Alright, so the insertion sort, what we looked at before was the selection sort, and you can probably remember this by selecting an item, swapping it with an item. Selecting an item, swapping it with an item. So it's true to its name. So insert an item. So insert orders a list by values by repeatedly inserting a particular value into the sorted subset of the list. Notice in this particular item, this particular selection sort, it would work nicely on an array because you're not having to reorganize the list. You don't have any holes in the list. The list is items 0, 1, 2, 3, 4 that may be array indexes, and you're switching them after you're finding it. So you're looking at this number, you're doing a loop to find this number, and you're swapping this number with this number, and you're not actually having to reorder anything. It's just a actual automatic kind of replacement that's going on, which actually makes it efficient. So more specifically, if we're doing an insertion sort, we consider the first item to be sorted, subsetting of the length 1. And this is kind of a subjective thing. We always start with the first item in the list. You could start with the last item in the list too, and work the opposite direction. It's just most people start at the beginning of the list. So there's no law that says you have to, though. So you can consider the first item and the sublist of length 1. Insert the second item into the sorted sublist, shifting the first item if needed. Insert the third item, because now you went to 1, 2, now you got the third item into the sorted sublist, shifting the other items as needed. And then repeat until the values have been inserted until their proper positions are achieved. Same list. So 3 is sorted. 3, there's nothing to do. 9 gets inserted, so because 3 is before 9. So 3 and 9 are sorted. In terms of the 9, it shifts to the right, and you insert 6. So you're shifting and inserting, shifting and inserting. So if 1 comes up here, 3's got to go over here, 6 has got to go over here, 9's got to go over here. So you have a lot of movement going on, more movement than you had. You don't have any holes created or anything, but you have a lot more movement created than just the swap of 2 items. More processing having to actually occur in terms of the programming of it. 3, 6, and 9 are sorted this way in terms of, this is the insertion, because you're taking this one and you're inserting it at the beginning, inserting it at the beginning, and then shifting everything over, because you have to make room for it. So if you didn't have to shift it over, if you had a linked list structure that wasn't doing any shifting, you just delete it. So if 1 was over here, delete that node, reconnect it, put it over here, put it in front. There's no shifting. In an array structure, there would be shifting. So depending upon how it's implemented, this could be very efficient if we're being used with a linked list type of structure. More efficient in terms of getting rid of the shifting time, because this is time consuming. We're just going to add time to the algorithm. So 2 is at the end, 2 comes in here. We put 2 in front of 3 and we shift everything over. So we have the same list as same result as before, but we're using an insertion sort method instead. And stop me if you want any more information on any of these, but they're pretty straightforward, I believe. The bubble sort. So the bubble sort orders a list of values by repeatedly comparing the neighboring elements and swapping their positions if necessary. So more specifically, we scan the list, we exchange adjacent elements if they are not in a relative order. So if they are in the order, we don't have to exchange them. Bubbles the highest value to the top and scans the list again, bubbling up to the second value, repeating until the elements have been placed in their proper order. See what this looks like. Oh, there's no bubble. Well, we're taking more than one item, so we're taking them in groups instead of doing them singularly. So if you looked at it, it's very similar to the one we just looked at a minute ago in terms of the insertion, but we're exchanging the adjacent elements. So we're taking more than one item, the adjacent element. So if they're not in relative order, if they are, we're keeping it. If not, we're shifting it, we're moving it. So the highest value is going to be at the top eventually. Kind of goes like this. In fact, if you were to imagine it, think of it instead of a linear, think of it as instead of a horizontal, think of it as a vertical line, and you're moving stuff, which is why they call it a bubble, because it bubbles up this way. So you're eventually shifting chunks of it up. You're saying 1, 2, 3, 12. Okay, wait a minute. 9 to 15. Oh, 15. Take 15 down and bring it up. So you take that down and bring it up. If you're sorting highest to lowest in that particular example, if you're doing it the other direction, then the top is good. You don't have to move anything until you hit a number that's out of sequence or out of bigger than, or smaller than what you've looked at already. Then you move that up. So, and then you can move more than one in terms of if you have one. Let's say you're at 9 and you're trying to do this. The top item is 9, and you're going through the list and you find 1, 2, 3, and then you have 12. Well, 1, 2, 3 are all below 9. Move those guys up. So you don't actually have to do three separate operations for that. You essentially just did one, which cuts down on the search space. Comparing the sorts. So let's take a look here. So we've seen 3 of the sorts so far. We've seen the insertion sort, seashells, no, she sells, I can't say that, I can never say that. The S's, so, selection sort, insertion sort, and bubble sort. So they're all used in nested loops, and they perform approximately end-to-end comparisons, because you've got to put a loop inside of a loop, because you've got the loop of the outer list, and you're looking at the inner list components, and you're putting them back into the outer list. So it's usually a nested list thing. They're relatively inefficient because we're using loops for it and we're nesting the loops. So we'll turn our attention to a more efficient sort. These are good sorts for small search space problems. When the search space gets big, there are more efficient ways of doing the sort. The sorts are not wrong. It's just that they're not that efficient in terms of large number crunching. So, Quicksort. Better option is kind of like the binary search. The Quicksort, although implemented a lot differently, fixes a lot of the inefficient problems of the double looping and the movement or the shifting. So it orders a list by values by partitioning the list around one element, and then sorting each partition. So that's why I say it's kind of similar to the binary thing. It's because it's essentially reducing the sort space while you're doing it. So you have fewer items you actually have to sort, rather than looking at each individual item. So more specifically, you choose one element in the list to be the partition element. Organize the elements so that the elements is less than the partition elements are to the left, and then they are greater are to the right. So if I were to take all of you guys and say, I'm going to order you guys by alphabetical order of your last name, and I'll pick the middle of the alphabet, or I'll just pick one spot in the alphabet. I'll just say Q. No, that's towards the end. I don't know. M. Everybody who's less than M, stand over there. Everybody's greater than M, stand over there. And then I've separated it out, and I've got it partly sorted. It's a quick way of getting everybody separated. So you apply the Quicksort recursively to both partitions. So you pick an item and you sort it, pick an item and you sort it. So the choice of the partition element is arbitrary. As I said before, if I probably would go in the middle, I don't have to. In fact, most last names don't start with Z. Most of them start with the first part of the alphabet. I don't know, maybe P, S, Q. I did this once for a final exam, actually. I tried to sort the list of students, and I discovered that they're mostly in the first part of the, I had like a lot of groups for the first part of the alphabet, and then the last part of the alphabet, past about M and N, there's nobody. Like a majority, like just only 2/3 of the students are before M, and the 1/3 is after M. So it's really not in the middle. For efficiency, it would be nice if the partition elements divided the list roughly in half, because then you're sort of defeating the purpose. If you take one item in the list, okay, all you guys are over there. You're not making the search space any smaller. Algorithm will work in any case, however. It just won't be as efficient. So we will divide the work into two methods. We'll have a Quicksort that performs the recursive algorithm that sorts, and then the find partition that rearranges the elements into two different partitions. So it's kind of a two-step process. And our code for this is going to create the partition and then sort the left side and then sort the right side. So we can say if we were sorting names in alphabetical order, we could apply the same approach until everybody was actually standing in the right order by going to both sides and into both sides. And then the find partition, if we were sorting the item and we have an item that we needed to put in there and to figure out which partition did it belong to, we do a simple comparison, and we compare the object of the partition element to see if it belongs in the grouping. So a couple of students showed up late. They weren't in the first sorting. And you say, well, what is your last name? Q. Okay, you're over here. And basically you find the partition that they belong to, and you put them in the partition. So, which is what you're doing when you're initially dividing the list as well. You're finding what partition you're going to find. How you define the partitions, totally up to you. It's how you're going to essentially. There's no science to it. You're going to get roughly the same equivalence in terms of the efficiency, as long as you're making some separation in the group and partitioning in some fashion. Okay, so for searching the elements, moving an element to a partition, left to right. So that one is the Quicksort. It's quick. So then you can think of the quick, if you want to remember, it's sort of like the binary search. It's very efficient. It has about the same kind of characteristics in terms of cutting things in half, but it's called quick because it's like quick and dirty. It's like you just take everything, okay, half the over here, half the over here. It's kind of like if you had a bunch of papers to grade, I give a stack to you, give a stack to you. I've just sorted it out. I've basically divided it out easily. Merge sort. A little different algorithm. So the merge sort orders a list of values by recursively dividing the list in half until each subhalf has one element and then recombining them. So it works off of the quicksort concept in terms of the efficiency of separating out the search space, but it breaks it down into smaller elements and then merges these smaller elements back into the bigger picture, which could essentially perform a little bit more time, but it may also be a little easier to actually kind of construe. More specifically, divide the list into roughly 2 equal parts. So you don't pick an item, you just say, take this list, put it over here, take this half, put it over here. So you're not finding a middle. You're not doing any criteria to select the partitions. I'm handing you a stack of papers, and I'm handing you a stack of papers. Recursively divide each part into half, continuing until the parts contain only one element. Merge the 2 parts into one sorted list. So you got 2 separate lists, and then you got one main list that you're creating with the separate elements that you've gotten out of the smaller lists. So you continue to merge parts as recursion unfolds, and you eventually run out of items. Let's take a little bit here. So the decomposition of the merge sort. We have 305. We're going to put this in, looks to be, I don't know what order, separated out. We took the first 3, stuck them over here, we put 4 over here, so we have uneven partitions, no problem. I believe what we're doing is we're putting this in numeric order, actually, because we're going smallest to largest, smallest to largest. And then we would merge these 2 together. We would take, because we have 7 over here, we have 8 over here, so we have 65, which is smaller than these guys. So these guys would still need to be merged. But the decomposition of the merge sort sorts it out, takes the biggest number out, takes the biggest couple of numbers, smallest number, kind of rearranges them, breaks them out into smaller components for comparison purposes, so that we can compare the items for some sort of a sort criteria. And then the merge portion, to put it back in together, the algorithm themselves, we end up with the 7, the 65. We merge the lists back in the right order. We merge that list back in the right order, and then we merge both lists together in the right order. So it's it's a 2-phase. You got to break it out and you got to put it back together, which is why they call it a merge, because you're separating it out and then you're merging it back together in the right order. Not going to work too well with an array element, probably with an array list. Probably going to work very well with a linked list structure, I would say. Because these can become 2 separate linked lists. Because essentially what you're doing is you're taking the list and making more lists out of it, taking all those lists and merging them together in the right order. So you're not swapping, you're not moving, you're not you're doing comparisons, but you're doing fewer comparisons than you would be doing if you were taking each element line by line. So no swapping and no insertion. So. And here's our lovely source code for that. There it was. It's gone. Nope, there it's going to continue. Here we go. Let's look at the efficiency comparing the quicksort with the merge sorts. Both of them use recursive structures, and they take the same amount of efficiency, log 2 to the n, for processing steps to decompose the original list into the list of length 1. At each step, both algorithms either compare or merge on all of the n items, so both of the algorithms are out at n log n. So they're about the same in terms of the efficiency. It depends on which abstraction you like better. Do you like that abstraction, or do you like insertion sort abstraction? It's nothing more than a level of abstraction applied to the concept of what you're doing in terms of the search. A lot of people like the merge sort a lot better, actually. Because it's easier to do. You have subparts of it, and it's easier to combine the subparts sometimes. So I can see where if you had objects of unliked kind, you could take all of the students and sort them out, all of the teachers and sort them out, and then merge the teachers and the students together in a sorted list following. So to combine it in the end. So, or you could use it for special purposes, I would think, in some cases. Radix Sort. So now let's look at one more sort that makes use of queues. So a Radix Sort uses queues to order a set of values. So we got a queue. A queue is created for each one of the possible values of a position or digit in a sort key. So we got a queue that's created for the key comparison. For example, if the sort key is a lowercase alphabetic string, there would be 26 queues for each one of the lowercase alphabetic strings that you're using. So if the sort key is a numeric one, there would be, let's say, it would be 10 queues corresponding to 0 through 9. So each pass through the sort examines a particular position in the sort value, and the element is put into the queue corresponding to its positional value. So it finds it taking a key, comparing it against a list of values, and sorting it per its position. So processing starts with the least significant position, the ones, and then the most significant position, or the end. Following example uses integers with only the digits 0 through 5. Alright, so let's take a look at the picture of this one. A little bit more complex to kind of imagine. We have 0 through 5. This is one of the problems with this particular sorting algorithm. Actually, it's easy to get wrong. It's easy to make a mess of the implementation. It's not the clearest, but it could prove to be more efficient in some cases. It's a little bit more advanced. So here I have the digits of 0 through 5. In the first position I have 420 and 250, and I'm saying that this is the front. And here's the 10th position, here's the 100th position. There's nothing right out there yet. So I'm going to take the original list here that got separated out into the first 10th and the 100th, into the 3 components or subsections. But these are separate lists, and the lists are going to be from 0 through 5 digits. So we have a 10 3-digit numbers that we're sorting in terms of the order of the particular list. And that one I'm going to leave because of the midterm. I'm going to leave you to actually do a sample pseudocode for, and I'll talk about that in a few minutes. Oops, what happened here? So here's the UML looking thing on how would we put together the source code for a Radix Sort algorithm. We would have an array queue, and these are examples. Let me go back and let me say something about this because I totally skipped. Hello. These would be like, oops, it's got a mind of its own right now. Let's see. I'll go back to this. It's a little graphic intensive. Hello, here we go. Here, let's go back to this for a second. My computer has a mind of its own. Hello. Where did I want to? Let's see. Hit it. It's technically challenged today. Let's see. Let's go back to the end. I'll just manually go to this, what I'm looking for here. Wow, it doesn't want to go back there. There it is, there it is. There. That's where I wanted to go to. What I wanted to say was that we have different lists inside of the lists. In each one of the lists, we would have a separate list for the 0s, 1s, the 5s, numbers that contain those numbers. And we would separate it out into different arrays. And in terms of the implementation, going back to that UML thing, we would have an array queue, using a queue for it, and we can switch the items around in the queue. We would have a default capacity or rear of the queue, and a beginning or head of the queue possibly, end queue, a D queue, a first element, it is empty, and then we would perform the Radix sort on it to move the items around in the various different queue elements that we created for each one of the items that we were sorting by in terms of the criteria that we were checking to get to the final answer, to get to the queue. So it's really an applied queue, essentially, a series of queues to get to a particular point where we can merge or use the queue separately. Is that the last slide in the slide set? Hello. Let's go back for a second. No, that is the last slide. Okie dokie. So let's hold off on that, and let me talk a little bit more about the Radix Sort a second. I don't want to save this. I want to show you something else actually before I get into it, because I don't want to answer all of your questions for you. I have put out on the okay, we had internet access. Ah, that uploaded. Maybe that is why my computer started running funny. Alright, let me go back for a second. I uploaded, this morning actually, the midterm exam and the CSLO essay. I want to talk about the midterm exam for a second, because it's going to be, when you look at it, you're going to go, 30 questions. It's worth 30 points. Each question is worth 1 point each. Everything is not due until 12/12 is the date we set. December 12th is the date that we set on this. Have a few comments to make on this, however. All of the questions come out of the book. So if you have a copy of the textbook, and I'm loaning a copy out to you, you can share it with your friends if you want. All of the answers to all of the questions are actually in the book, and they're also in the lecture sets, though, that come with the book. You can also find a lot of information on the internet. I'm not looking for a novel on the answers of these questions. I'm looking for a simple 1 or 2 sentence response. Not a lot, because you have 30 points, 30 questions, each question is worth 1 point each. Pretty simple, actually. It's just a regurgitation, essentially, of the information that's in the book. Of course, it's take-home and it's open book, open notes. But it gets you to kind of think abstractly about some of the different concepts. As an example, the first question here says compare and contrast data types, abstract data types, and data structures. Which you're going to have to kind of think of. Okay, so if you compare and contrast, you could probably write like 300 words or 600 words on that probably. Or you could write 2 sentences. I'm probably going to have 3, because you're going to say data types are this, abstract types are that, data structures are this, and data structures used are implemented in the form of abstract data types. And they use built-in data types to create the abstract data types. And, you could probably answer it, in so many words. However, I'm not looking for more than just a simple definition. That's one of the easiest ones. One of the more interesting questions, and this might be an issue for you, list the collections of the Java collections. List the collections in the Java collections API. Don't list everything. Give me just like a simple list of the basic ones. And I would just list them out. I would just go, 1, 2, 3. You don't have to write a complete sentence for it. You're not being graded on your grammar, your spelling, your punctuation, or your writing ability. Some answers can be answered in a few words. Some you can actually write a full sentence. Some you can pull a bullet list. The differences between the growth function and the algorithms and the order. I put in some of the questions for which you're probably going to need a little bit more information. I put the chapter numbers. And I only did this for chapter 2, actually. Because chapter 2 is the chapter that talked about the complexity and running time and efficiency of algorithms. Is the algorithms. And the entire midterm exam goes through chapter 8, which is the lecture I just finished. So it covers searching and sorting. And down towards the bottom, the questions get a little bit more difficult. What is it, the iterator? Hold on a second, I wanted to find one in particular. Here's one here. Write an algorithm for the add method that will add at the end of the linked list instead of at the beginning. So you have to imagine a linked list that has an insert or an add, a node into it, and you don't need to write a full program. What you want to, you don't even have to write source code. You can give me pseudocode, which is fake code. This is how you add it. Or you can give me real source code. No complete program, don't spend too much time writing a complete program to do this. And I don't want to see a cut and pasted linked list example off the internet. It's better if you just simply describe, because you're going to basically add it to the end instead of the beginning. So look for an example that adds it to the end and say, well, we position it so the next point's in a different direction or something. And what you want to do is sort of explain it. You don't actually have to write source code for it. In fact, none of the questions require any source code writing at all. And they're all theory-based. I shouldn't say they're difficult. I'm leaving this to you to figure out, which is why I'm not gonna give you the answer. How many queues would it take to use a Radix sort to sort the names sorted the names sorted as lowercase. You could just say names. The wording of this question is not so good. So if you had names, this should be sort names, people's names, stored as lowercase. So you have 26 characters in the alphabet, and you're sorting names by 26 characters. You would have twice as many if it were lower and uppercase. You can imagine that. And you're making it. So you can answer the question. I just gave you the answer, actually. How many queues you would actually need for that? But what you want to do probably to answer the question, if you're not listening to me right now, is to go through the chapter reading, actually, which is not bad reading. As I mentioned before, it's not a bad idea to read the book. The Radix Sort actually is fairly simple. It just takes a lot of queues. There's a lot of queue implementation for it. So it's not quite what I would call an easy implementation. It's actually kind of one of the more difficult implementations. It's easier to implement a lot of the other techniques for the sorting. Tree nodes, a little bit on trees, which I haven't covered yet. I'll be covering trees next time. In fact, we're going to go into binary search trees and trees concepts, which is going to be the theme for next week's, 2 weeks from now, lecture. And it ends on the tree elements. So the midterm exam is not due until the very end of the course. And the tentative due date I have set right now and decided on today was 12/12. We like the date 12/12. So. Questions about the midterm exam, you can get it from bhacker.com. It is not in the LMS yet. The LMS doesn't have it yet, but it will hopefully have it soon. The other new item that is out there available for you to look at is the CSLO essay. Unfortunately, however, it's not an essay. I shouldn't say unfortunately. I should say, if you don't like to write, don't worry about it. However, you can take a couple of different approaches with this. So it's worth 25% of the grade, a little bit less than the midterm. It says write a 2 to 4 page double-spaced essay. When I say it's not an essay, I'm meaning that you can supplement some of your page count with source code or with design code. We'll talk about that in a few minutes. Alternatively, you can provide source code with comments in the source code as well. So you could write a program, put comments in the source code, and submit that as your assignment. And the comments are going to be explaining, and I'm going to go through the questions in a few minutes. They're all pretty much the same, they're just on different concepts. Explaining what you've demonstrated. Your paper or source code must reflect your own writing. Cannot contain cut and pasted parts on the internet, so don't go out to the internet, cut and paste something, put it in there, add some comments, and go, here you go, it's done. It'd be nice if you actually did it yourself. And you can do it in any language you want. You don't have to do it in Java. Do it in any programming language you want. So what is it that we're talking about here? You pick one, select one, and you've got 4 options. I'll go through the first one because they're all the same. The wording is practically the same. The only thing that's different is the bolded letter. You're going to design a program that uses a stack or a queue data structure. Okay. Describe why you use this structure as part of your implementation. Provide a summary of the benefits and issues related to your chosen implementation technique. Provide either pseudocode or programming language source code to demonstrate your implementation. You do not need to create a full program to demonstrate your understanding of the concepts. So you can create a simple stack or a queue that doesn't do anything, that just doesn't like run in a program. But it's nice if you can apply it to something, but you don't have to implement it. As an example, we've had a lot of examples from the book that were associated with different types of games. You could do a stack that took and, I don't know, what kind of game would be, so that's your homework. You decide what kind of game would be appropriate for a stack. And then part of the assignment, part of the grade of the assignment is did you give me some reasoning as to why you did this way? But the functionality of the game doesn't have to work, just the stack or just the queue. And the concept is to document first why you selected it, what's good about it, what's not good about it. You can even ad lib it if you want to put some things in there and say, well, some alternative approaches would be this, this, and this, or something. Or you can certainly modify the requirement a little bit, customize it. You're going to do one of the four. The first one's a stack or a queue. The second one's a linked list. The text is the same for each all of these items. Or you can do a tree, or you can do a sorting or searching algorithm. So you can take, in terms of the sorting and the searching, maybe do a card game or something. That'd be fun. Search a deck to see, search a hand, or do some random kind of number card generation or something, and decide on what kind of search you'd like to do. It's like, is this card in the deck or is this card in the deck? You remember that game? You pull the cards out. Pick a card. And somebody picks a card out. And you put the card back in. You're sort of trying to find the card or something. You can be creative if you want. You don't have to do something that complicated. It's not really that complicated, but this is if you don't want to write source code, you can write pseudocode. If you're writing pseudocode, you're going to be doing a lot more writing. But it's a little harder, I think, to write the pseudocode than it might be just to implement it. If you want to use part of the assignments that we have that implement stuff, you can do that. So if you wanted to take a queue that you created, you can reuse your queue. The only thing is you need to add benefits, issues, and sort of apply it to something. We come up with a problem scenario, a game, an application for it. We say, this program keeps track of people waiting in line at the teller window at the bank. And I've selected to implement it in the queue because the first person who gets there should be the first person who gets served. And when they're done with this queue, they're going to go to that queue over there so that they can make an appointment for something. So you can have one queue, you can have two queues. You can mix it. You can put the linked list one's kind of an interesting one. You can mix the implementation and say, well, I'm going to create a linked list, and inside my linked list I'm going to have a node. The node's going to be a structure, and my linked list is going to be a class. You could talk about the implementation details if you wanted to, but you don't have to. It depends on your level of programming skill and what you're comfortable with. If you're more of a writer, you can treat it like a writing assignment and just describe it. And give me some pseudocode. Look, here's the link, here's the list, here's the node. Draw pictures if you want. You can draw, like if you wanted to include a UML diagram or something of your particular program implementation, your design, that would be acceptable as well. It would take up some of your page length, actually. Your page length is 2 to 4 double spaced, which is 1 to 2 single spaced. I'm not asking for that much. Yeah. Because it's really kind of a thinking. It's kind of a think and decide what you want to do, and it's all up to you. There's no right or wrong kind of way of doing it. Questions about the CSLO essay? Nope. Question about the midterm? Nope. Question about anything? Well, let me stop the video. So since we have no questions,